How your slab will be built. This is included in the plans, the negative box. In this case, some variable resistors are considered, and the client is also informed about all of this. All of this is provided with this level of detail. These are the positive boxes, how the positive is installed, how the welding will be done on the cable pipes. And this is another example of calculations for galvanic anodes, but for buried pipes. So also, like the calculation of the current requirement. First, the surface area is calculated. In this case, it comes out to 39 square meters. From this total area, you determine the percentage of exposed area and which part is covered. The exposed area is what we are going to protect. Based on this, we select the current density for that exposed area, and in this specific case, it turns out that with 0.28 amperes, those pipes would be protected. The number of anodes is calculated based on, in this case, the client required 20 years at 20 pounds, and according to this, the required quantity is determined. Next comes the number of anodes based on the current required. The resistance of the anode is also calculated according to the environment, and so on. Get familiar with this information because I want to go into detail with the calculation sheets, and the construction details are also included. I'm having a problem right now because the software is freezing, and I don't want to miss the chance to explain a spreadsheet live. Here I'm providing some additional information for when magnesium and aluminum anodes are used. And well, folks, let me repeat, I always upload my videos, my technical and professional training, to YouTube. I always document everything, all the records and all the work procedures, I share them. Subscribe to my channel, and every time I upload a video, you'll be notified whenever I post new information. Same goes for LinkedIn. I'm also very active on Lena's professional network. Now let's move on to the example I mentioned with the spreadsheet. Normally, folks, when we're doing our calculations, we always start by calculating the surface area. That's the first calculation we make in our design considerations. Pay attention in this case, I want you to focus. These are the diameters, these are the lengths, and these are the total areas. This percentage, the area to be protected, the required current, the safety factor we include, and finally, this is the adopted current. In this case, this is a 16-inch pipe with a length of 10 kilometers, and it requires 53 amperes. Let's look at the percentage. What exact percentage is it this time around, specifically? The crucial thing to understand is that this particular item or option is currently not being selected or highlighted for me, which is causing a bit of a problem or a point of confusion in the current process or display. Okay, for total area, it's taking into account 10%. It's serious to set 10% of the exposed area. Unless the client tells us, set that value for me. The client might say, let's consider 10% or 5%. But what do the standards say? What do the standards tell me? I don't want to get too tangled up with this. I'm going to check the standard. Remember when I mentioned the PDVSA table from the Institute of Scientific Research of PVS, that when it's 0 years, you consider 1%, and when it's 10 years, you consider 3 or 4%. Notice that selecting 10% of exposed area would be roughly equivalent to a pipeline that's been in operation for 17 years. That's why I say this is serious. So let's assume, for example, that this particular pipeline has a 1% error rate. What's the most common thing clients always tell us? A client will say no, consider 1%. So here, folks, I'm encountering a perplexing situation where, for reasons that are currently unclear to me, the system or process in question did not accurately capture or register the complete and total value that was expected or intended. This oversight is quite puzzling, and I am trying to understand why the full amount or entirety of the data was not properly recorded or recognized, leading to an incomplete representation of the intended value. It's a significant point of confusion as to why the system failed to incorporate the entire sum or all relevant components, resulting in an incomplete or partial capture of the overall value that should have been reflected. Let's put it here. Okay. I'm a bit tangled up, folks, because it's putting in values here that I don't want. Now, how exactly do I go about doing it, especially since it feels as though God has completely taken it away from me, and now, with a strong sense of urgency, I absolutely need to find a way to get it back into my possession. Alright, I've returned to version 1.8 of the software, and this time I am specifically using it with a tablet device, which provides a different and perhaps more intuitive user experience compared to other input methods. Notice that here, with 10 kilometers, it's asking me for 53 amps. What would happen if it were 20 kilometers? 20,000 meters, the current requirement doubles. That is, the length is an important value in our calculation. What if it's 1,000 meters? That would be 10,000. Sorry, 10,000 is 10 kilometers. For just 1,000 meters, it would only be 5.3. Let's leave it at 10,000. 10 kilometers, 10,000 meters, that would be 10 kilometers, 53. But in the area to protect, we're going to set it. Here it has 10%. Remember, we're going to set it to 1%. The client told us, no, consider a 1% response for me. Out of 53, it dropped to 1. Do you truly comprehend and fully realize how critically important that specific value actually is? What precisely happens? What are the immediate implications if I were to meticulously set it to a mere 3%? But what I genuinely desire and ultimately want to achieve is to have it precisely set right here, at this exact point. For this one, I'm going to set 3% of 5.3, please. Look here, now I'm going to change it to 3%. It tripled. This means that the value we select for exposed area significantly impacts our design. But now let's move on. That's with the exposed area. That value is either given to us by the client, or we should go out to the field with a portable plant, a portable car battery, inject current into the pipeline, measure the potentials, calculate the current the pipes are consuming, and use that actual current density. When a pipeline is brand new, never built, never buried, we have to assume these values. What do international standards tell us? I'll say it again, either the client defines it or we go with international standards. So if I go by international standards, well, I'll assume what NE says, what ISO says, and I'll choose the most conservative one. In this case, a 3% response is conservative, because I know many companies that have installed high-performance 3-layer systems and the coating systems have failed. Now let's move on to the required current. What do international standards tell us? Notice that, depending on the environment, the corrosive environment, when should I make a selection? Because notice that here it talks to me about the coating as a factor. If it's a coated pipe, I should. If it's a 3-layer system, I should. The most severe would be 0.2. But what happens if, according to the physical-chemical analysis, I have the presence of chlorides, sulfides, nitrates, and it's a highly corrosive environment, or it's submerged in water, salt water? In salt water, it mentions 43 to 54 milliamps, but it also mentions 161. There are other standards. For example, this is the NACE table. This table is in NACE, and for coated steel it mentions 0, 0.2, but it also refers to the environment, including when the pipes are bare. Take a look at this table over here. This is a table of criteria for cathodic protection systems based on the environment. In Venezuela, for example, in Lake Maracaibo, you should select between 50 to 100 milliamps. Take a look at this other table for the Gulf of Mexico. In the Gulf of Mexico, you can see that 110 milliamps are required initially, 55 as an average value, and the final value stabilizes at 75 milliamps. So, there are tables for Brazil, for example, where 180 milliamps are required, with an average value of 65 and a stabilization value of 90. So here's where the big detail comes in. Notice how the equation is affected. Remember that we selected 3,000 square meters of exposed area, right? Here it is, which is this one right here, 3,000 square meters. Now let's look at the required current. In this example, the pre-required current is 32. What happens if I set it to seawater and put 80 milliamps? Let's see how the current requirement changes now. It went from 15 up to 39 amps, so notice how the decisions you make significantly impact the design. Why does it have such an impact? Because going from 15 amps to 39 means a higher requirement, more materials, more anodes, more cable, greater rectifier capacity, and this increases costs. So obviously, these are the elements, the two main characteristics that affect our design. So, the safety factor. Let's see what it is here. The safety factor here is 30%, a 30% safety factor. Sometimes the client might say, no, that's too high, set it to 20. Well, that's fine, you can lower it to 20, but don't go below 10. The safety factor is always something for you. It's a cushion. So if you end up short on exposed area or current density, that cushion might just save your engineering. So you should always take that safety factor into account, because what if you selected 3% of responses but in reality it's 5? Then you'll need more current, and the safety cushion, the safety factor, is what can still support your engineering. The same thing happens with the required current. Maybe you calculated 35, but it turns out that in reality you needed 50 milliamps. So that safety cushion, or safety factor, is what can save your engineering work. So always stick to your point. Don't just look at things based on the conditions, unless you were the quality assurance inspectors during the pipeline construction phase, and you made sure that the coating was in perfect condition, that a holiday detector was used, that everything was flawless, and you can guarantee, no, look, I only considered 1% because I'm sure the pipe is fine. If that's the case, then you can assume the 1%. If you're not sure, don't. And you know how construction processes go when the supervisors aren't around, when the owners aren't there, when you notice the contractors looking the other way, they didn't put a heat shrink sleeve on the joint, and now you've got corrosion problems. So those two factors, that's why I wanted to do the calculation, so you could see what happens when one value or another changes. But let's look at something more interesting. I'm a bit tangled up on how to download this table. Let's stick with our same example for now. In this case, we kept our surface area at 1% of the required current. We set 80 mils, so what do we need? For these two pipes, we need a total current of 57 amperes. Now, let's look at these values. If I calculate the required amount based on the service life of this current, 57.8, which is this one here, it gives me a total of 22 years. This is based on service life, but here it says 25 years. And this utilization factor, this is usually given to us directly by the manufacturer. But let's say the client specifically told us he wants a full 30 years for this particular table. Because when I want to precisely set the value, then, well, let's say the client clearly stated, no, I absolutely want a service life of 30 years. Let's carefully see how much this extended number of years truly affects us, a significant 30 years. It went up from an initial 21 years to a full 30 years, representing a considerable increase. So notice that if the client takes a stand and tells us 30 years, the number of required anodes is affected. In this case, let's leave it at 25, it's still at 22 years. I want you to see, step by step, how all these numbers are affected. Required anodes based on discharge current. Based on the discharge current, with 12 anodes, those 57 amperes with 12 years, we could get the system up and running. But really, if the client set this useful life limitation, I can't do that anymore. I have to rule this out. This doesn't apply because the client made their position clear and told me, no, I want the system to last 25 years. So now I have to select this. This takes precedence. If the client says 30, well, we already know it goes up. But this is based on the current density, the drainage capacity. Here is Dwight's equation for calculating the resistance of vertical anodes for several vertical anodes. In this case, it's giving us a 88. Notice how this table is giving me this value. Remember that for useful life I should assume 22 anodes, but will the system really work? Let's consider another very important and crucial detail. It turns out that with this current and specific requirement, the 57 amperes of electrical current we absolutely need for 22 anodes, specifically 22, up to this point, 22 individual anodes, which is precisely this particular one right here. We are going to require a rectifier with a voltage of 11 volts. So, the question arises, is it truly feasible, based on that current and demanding requirement, to effectively utilize that specific number of anodes? Will it genuinely work? Will it properly function as intended? Because in the broader market, I can potentially select a rectifier with a voltage of 20 to 30 volts if such an option is readily available, along with that corresponding amount of electrical current. But look, let's do another exercise. This is in the case where the anode, or the setup, is going to work with a resistivity of 1000 ohms. Here's another critical mistake in the field. Designers trust the values provided by clients. Ladies and gentlemen, you have to go out and measure this in the field. I've come across cases where they tell me it's 1000, but when I go measure in the field, I find resistivities of 20,000. Let's use 20,000 now. But let's go back for a moment. With a resistivity of 1000 ohms, here I already have Ohm's law equation adapted to these values. And for a single anode, I would need 142 volts. But what happens when I use 20,000, resistivity of 20,000 ohm centimeters? It jumps up to 815 volts. Finding this in the market isn't feasible. This would require a custom build, a special design. So notice how resistivity affects my calculations. Now let's see what voltage you get with 22 anodes, depending on the service life, with 22 anodes. I keep going, keep going, keep going, keep going, keep going. I need a rectifier of 196 volts, that is, almost 200 volts. You can't find that on the market. Maybe you can get a 100 volt rectifier. So, with 22 anodes, that's just not feasible for me. What does that mean? The current stays the same, I still need 57 amps. I can't change that. The resistivity is fixed, I can't change it, I can't modify it. But I can change the total resistance of the circuit, meaning if I increase the number of anodes. Let's see how many anodes we need for 100 volts. Look at this here, this I can actually get on the market. Maybe let's set it at 95 volts. How many anodes would we need? So, 49 to 50, then in the design I have to select this number of anodes in order to be able to get this rectifier on the market that can supply me with 57 volts. Did you notice that this value messed up everything for me? The whole calculation and the design? If they give me this resistivity, if this is the real resistivity, 20,000, but out of laziness, negligence, or incompetence, I left it at 1,000 because that's what they told me, the system won't work when I install, build, and start up the system. But the system didn't work, of course, you had a false resistivity. You had a false resistivity, it's not going to work for you, it can't work. Let's keep going, let's set it to 1000, notice that it's at 142 here. What happens if the length of the anode, this is a 3-meter anode. What happens if the length is 6? In other words, I installed double anodes. The anode is 1.5 meters long plus 50 centimeters of coke at the bottom and top, so it's about 2.5 meters. If I put in 2 anodes, that would be 5 or 6 meters. Let's say the anode is going to be 6 meters long. Let's see how much the voltage is affected or how much the equation is impacted. Let's set it to 6 meters. Look, we have 142 here. We have 142. Now the voltage requirement dropped because the resistance increased. The total resistance of the circuit is decreasing. So in the equation, this length has an impact. It matters. Notice that from 50, let's look for the 50 to see how the resistance was. It was at 95. See how it dropped it to 5. That means, if I were to go higher, just look at this particular voltage, which is 81 volts, with a rectifier that provides about 150 volts. I can comfortably handle up to 160 volts, so I can effectively manage and ensure the full 22 years of useful operational life for this component. Here, I can still maintain the useful life. I would need a rectifier of 10 volts and 60 amps. Notice how the math changed for me, it impacted the design. That means this value matters, resistance matters. Length doesn't matter. Let's see how much the diameter adds or affects things. This is a diameter of 20 centimeters, but there are drills that can handle 30 centimeters, 0.3. Let's see how much that affects things. I have 81 volts there. Let's see if it made a difference, if it improved anything. It dropped it to 73, so for the 22 years, with a useful life calculation of 25 years, 8.5, it didn't really affect it that much. Here in this equation, I also have the calculation for the coke required for each one. Notice that when I set it to 6 meters, I needed 223 kilos, but when I set it to 3 meters, for 3 meters of anode I need 111 kilos. I also calculate the equation, plug it into the equation, and the anode spacing as well. So notice that resistivity, anode length, and anode diameter all have an effect. So, our decision-making is indeed impacted. Each of these values must be considered, and what we're really looking for is to have a viable value for voltage and current. We already know that the current can't change. There it is. I need this. So here, instead of 57, I assume 60, I need 60 amperes. But I have to look for a voltage that's commercially available, that's easy to manufacture or readily available, so usually I set myself a target. Well, I know that in the market, a CI 100 rectifier is common, a 50 to 50 rectifier is common, a 30 to 50 rectifier is common, so I try to adapt to what's available on the market. That's why we have to adapt our calculations to that, to what's viable. If I don't take that into account, look at what could happen. If I assume a receptivity of 1,000 and in reality it was 30,000, then when I build it, it won't work. Notice that with 30,000 ohms here, I would need a rectifier of 3,737, so when considering the weight, well, I'm working with a table, and it's not the same as handling it directly, but I think you get my point with this message, folks. Every decision, every value, every concept we assume, exposed area of material, current density, whether it's due to the environment or the quality of the coating, soil resistivity, the length of the anode, the number of anodes, if I increase the number of anodes, the resistance goes down, and if the resistance goes down, obviously that's going to benefit my circuits. So, clearly, all these considerations affect our design. I hope this has served as a guide and introduction for you. And well, if you have more questions or need further clarification, don't hesitate to contact me via email. As I mentioned, subscribe to my YouTube channel. You can also reach me there or through LinkedIn, and I'll be happy to continue expanding your knowledge on the subject. Once again, it's been a pleasure, and I hope this is useful to you and a valuable contribution.